Hello, everyone. Today's lecture is going to be on 15.2, which is integrals on general regions. So in 15.1, we just started dealing with integrals for these multivariable functions, integrals when our domain is more than one dimension. And we only did integrals on rectangles. And now we're going to kind of expand that because that would be really limiting, right, if we can only integrate on rectangles. So we did learn how to integrate on rectangles last time, and that's all well and good. But we encounter a problem with higher dimensions that we didn't have in a single dimension. Okay, so if we think about integrating a function of a single variable, right? The thing we're integrating on, if we're thinking about a continuous, like a single chunk of where we're going to integrate, it can really only be an interval, right? We have, and we can really think of this in terms of boundaries. So when we have just when we're integrating just on this line, this x-axis, what's what could our boundary possibly look like? Our boundary is just these two endpoints, right? And so if we're integrating everything inside the boundary, that can only be an interval. Okay, so that's fairly simple. But the multivariable boundaries can be a lot more complicated, right? Because now I have, when I put two dimensions together, for example, if I just add one more dimension, then I have all these two-dimensional figures that my boundary could be. So the yellow line here is our boundary, and maybe I want to integrate on this region, so everything inside this boundary. Okay, so last week we learned how to integrate on the rectangle, right? We learned how to integrate on something, like if I kind of expanded that region to be here, I know how to integrate on that. But what about just a triangle? Okay, and this is still fairly straightforward because okay, something weird's going on here on the slanted line. But then if I'm looking at the x-axis, this is still just an interval, right? It's like from A to B. And then maybe if I'm integrating along y, something funky is going on. All right, so that's still a fairly simple case. And we could have even more complex cases where, okay, this is a figure, this yellow figure is in the xy plane, and we need to integrate on that a function on that shaded region. Okay. So how can we deal with these cases? So let's talk about theory first, and then we'll talk about practice. So the integral we defined in the last section was defined on rectangles, and we want to avoid having to kind of recreate a new integral for every possible shape of our domain. So what we're going to do is we're going to start with some sort of a regular shaped domain, whether meaning not a rectangle, and we're just going to make it into a rectangle. Okay, so that's our simple fix. Our simple fix, let's say I want to integrate this blue function on which has our yellow domain. Okay, how do I integrate that? It's not on a rectangle. I'm just going to enlarge that yellow triangle into a rectangle. Okay. And how I'm going to do that is, well, if I'm enlarging the domain, I have to define my function there. Like, let's say I'm trying to, make this into a rectangle. Okay, what is my function going to be here then? And how is that not going to affect my integral? Okay. Well, the trick is we're going to make this domain into a rectangle, and then we're going to call our function, which is our blue surface, we're going to just say it's 0 on that kind of enlargement. So here we have our original function, and it's taken all kinds of values. And then we've enlarged our domain here. And then everywhere inside this kind of enlargement, we're just saying, okay, f of x equals 0 there. Now, this might seem a little confusing, like, why are we doing this? And doesn't this kind of screw up our function? Well, no, not really. It's we're only doing this for the purposes of the integral. So we can see, first of all, that this function is probably not continuous, right? But that doesn't even matter. We can integrate functions that are not continuous as long as the discontinuity is not too bad. Okay, so here this discontinuity, it's actually kind of, in some sense, kind of well behaved. It's not super jagged or anything like that. It's just kind of a smooth discontinuity, and it's not it doesn't present a problem theoretically. Okay, and as long as we make our function 0, it's not going to affect the integral, right? I can think about integrating on this rectangle. Okay, if I integrate here, what is that giving me? It's like the volume underneath that surface, right inside that original yellow triangle. And then if I'm adding this region, if I'm adding this area where my function is 0, okay, that's not going to affect the so-called volume I'm trying to find, right? Because there's going to be no volume in between my blue surface and my yellow rectangle, but it does give me a nice rectangle to work on. So as I said, the function might not be continuous now, but that's not a problem. Okay. And once we have this rectangle, we're going to be able to use our theory from 15.1, where we define this integral as the limit of Riemann sums. So the theory is going to be unchanged. Okay, and that's really all we need to say about the kind of theory behind it. We're taking these weird domains and turning them into rectangles. And maybe one more piece of information. This works even if, we saw a triangle, turning a triangle into a rectangle. That was fairly straightforward. But even if we have some kind of weird domain, it still works. So let's say my domain in the XY plane is like kind of this kidney shape here. I just encase it in a rectangle. So let's say my function on this kind of kidney shape is, something like this. Okay. All right, I just slap a rectangle around it, essentially. Okay, I call this rectangle in the XY plane my new domain, and then my function is 0 everywhere on that enlargement. Okay, so still works. Now we're going to see a couple ways that our region might not be a rectangle, and how we approach it depends on how it's set up. Before that, I'm going to have to take several little breaks here as I record this. You won't even notice it. Continuing on. All right, so we were discussing the types of problems we can encounter with our domain. Okay, so generally speaking, we divide them into 2 types. These are kind of the basic problems we might have with our domain. I shouldn't call them problems because they're really there's nothing problematic about them. But these are the kind of 2 non-rectangular. These are the 2 types of non-rectangular domains we might see. Okay. So we're going to call a region D in the XY plane type 1. I'm missing the numeral 1 here. Type 1. If it's bounded above and below by functions of x. Okay, what do I mean by bounded below? So let's kind of write our XY plane here as we would normally: x horizontal axis, y vertical axis. So our type 1 domains are regions that have as an upper bound some curve, which is written as a function of x. Okay, and then the lower bound, as we could also write as a function of x. Okay, so what does that look like when we add in our z-axis? Okay, so we might see it we might draw it like this. Okay, so we have the same exact domain. I've just drawn it in the three-dimensional plane instead. Okay, so here we have our lower bound g1 of x and our upper bound g2 of x. Okay, so the upper and lower bounds are written as functions, and then the right and left bounds are just constants. Okay, and that's when we're describing a domain, that's what we need, right? We need something above, something below, something to the left, and something to the right. You know, broadly speaking. Okay, so in type 1 domains, our upper and lower stuff are written as functions. Okay, and they're going to be functions of x. And then our left and right, our bounds for y, are just going to be constants, like a to b. Okay. Okay. Now, how do we integrate on this type of region? We're going to use the iterated integral just like we did in 15.1. So we're going to we're going to go from something like this, an integral like this in this kind of general notation, and then we're going to turn it into an iterated integral. So we're going to break it up into integrals of x and y. Okay, how do we do that? Well, let's see, going back up to this domain, maybe the x bounds are easy. Okay, my horizontal bounds, I know my x value is between a and b, so maybe those should be my domains, or excuse me, those should be my bounds for my domain. Okay, so I'm going to start by writing integral sign a to b there. Okay, what about my y bounds? Okay, so my y bounds kind of correspond to my vertical stuff, right? So what is my upper bound, my upper vertical bound here? Okay, that's that function g1, right? And then what's my lower vertical bound? G2. So let's use those functions as upper lower bound, and I got these backwards. Okay, it should be G1 and G2. Okay, so I'm going to use as my y bounds G1 of x in the upper bound and G2 of x in my lower bound. All right, so what does this mean? So if you kind of think back to one of the ways I said you could think about these multiple integrals in 15.1, what did I say? I said you could think, let's see, if we had a surface here that corresponded to this domain. Okay. I want to find the volume, but you know, intuitively speaking, I want to find the volume beneath the surface. So what's one way to do it? One way to think about it is to take slices going this way and finding these integrals and think of them as our normal integrals, right? So I kind of lay this slice flat on the page. What does it look like? It looks kind of like this. And then what is the integral of this? Let's see, my upper part of this would be what? Excuse me. It would be my function fxy, but where my x value is what? If I'm talking about the very end here, my x value is always a. Okay, and then my y value is varying, and what does it vary from? It varies from this point to this point, so it kind of goes from g1 of g1 of a to g2 of a. And actually, I wrote these backwards as well. This is G2. Yeah, okay, I had that right. So this is G2 and G1. Okay. And then, so that gives me the area of one slice, and then I integrate going down this way. right? And that I add up all my slices and I get my total volume. So it's like I should be integrating G2 to G1 of X. Okay, that's giving me the area of these slices. And then I'm integrating down along my x-axis from A to B, and that should give me my total volume. So that's how you should think about that. Apologies. So as I was saying, when we have this type 1 domain, our vertical bounds are functions of x, and our horizontal bounds are just constants. Okay, and so what this is saying is that we're going to have an integral, okay, where we have a to b integrating in terms of dx, and then our bounds for y are going to be these functions of x. Okay, and a way to think about that is usually for these functions we would write like y equals g1 of x, right, and y equals g2 of x. So think of it like this: our y bound is going to be that function. Okay, upper and lower y bounds will be these functions. Okay, so let's see an example so you can start to get a feel for this. Let's try and integrate this function x squared y on this domain. Okay, and this is one of the possible ways we might be given a domain. So this is in the set notation. So we're told our domain is all the points x and y, where x is greater than or equal to 0 and less than or equal to 1, and y is less than or equal to x and greater than or equal to x and less than or equal to x plus 2. Okay. All right, so we see our functions here, right? These, the x and x plus 2 are functions of x. Okay, so let's do a quick sketch of this domain to see what we're looking at. And all we're sketching here is the domain. We're not sketching the function. So we're just sketching the area on where the function lives or is defined. Okay, so what is the curve y equals x? Okay, that'll be this. And then what's x plus 2? It's the same line, just shifted up 2 units. Okay, so this is y equals x, and this is y equals x plus 2. Okay, so those are our kind of vertical bounds. Those are our bounds for y. And then what are our bounds for x? Well, x equals 0 to x equals, let's see, if that's 2, then 1 should be right about here. Okay, so these are our bounds. Now, there's only one, if you feel like this is ambiguous, there's only one region that is totally enclosed by these conditions. It is this shaded region here. Okay. All right, so we're integrating this function on that region. All right, so now how do we set up our integral? Well, our type 1 integral, as I said, the x bounds are going to be constants. Okay, and when I'm dealing with these functions and bounds, okay, the function stuff is always going to go on the inner integral. Okay, so let's see, I'm saying my x bounds are constants, so that's going to be my outer integral. And what are the constants? Just 0 to 1. What's my inner integral? Okay, that'll be the integral with the functions in its bound. Okay, what's the lower bound? Well, think about this. Look at this region. Think about all your y coordinates. They're all greater than this line, right? They're all above this line. All our y coordinates all our points are above this line. So that bottom bound should be this line. Okay, y equals x. And I'm not going to write y equals x in my I'm not going to write that in my lower bound. I'm just going to write the function of x, which is just x. Okay. Now, what's my upper bound for this region? Okay. I again look at all my points. They're all below this line, x plus 2. Okay. They're all below this line. So I'm going to use that as my upper bound. Okay. And then I know my order of integration. Okay, this is my integral for y, and then I have my integral for x. And then what I would do, I put my function that I'm trying to integrate inside there. Okay, so this is how I set up my integral. And now let's see how to solve this integral. Okay, so this is a little strange because you've probably not had too much experience with functions in the bounds of our integral. Okay, so my first step is to integrate this in terms of y, and I do that normally. Okay, I find the same antiderivative I would normally. Okay, so I have 1, 0. What's the integral with respect to y of this? It will be x squared, y squared over 2. And then I would evaluate it at my bounds. And now, what are my bounds? Well, my bounds are x plus 2, or excuse me, x to x plus 2. Okay, so I have this. And then just plug your bounds in for y. Okay, so when I plug in x plus 2, I get, for y, I get x plus 2 squared over 2 minus, x squared over 2. Okay, and now this is all still inside my integral for dx, or excuse me, my integral of x, right? So what I'm going to do is I'm going to simplify all this, and I'll just end up with a function. And now there will be no y's. There's just going to be x's, and so I'll be able to integrate that further. Okay, so let's see. I have x squared times x squared plus 4x plus 4 over 2 minus x to the 4th over 2 dx. Okay, multiplying that out. Okay, my x to the 4ths cancel. I'm missing an x there. X squared, actually. Okay, and now I have this integral. And now this integral is just an integral of x, and that's easy to solve. That's everything we've been doing in Calc 1 and 2. Okay. And now evaluating this integral, I have, say, 1/2 plus 2/3, which is equal to what? 5 over 6. Okay. Now there's going to be more examples of these type 1 integrals, but first I just want to hammer home what we're doing here. Okay. So I have a domain. Okay. And the domain has these boundaries, okay, where the y coordinate is bounded by these two functions of x. Okay, and what we call them doesn't matter. I'll call them h1 of x, h2 of x if you want. So the y coordinate is bounded by these two functions, and then the x coordinate is just bounded by constants. Okay, so that's what we mean by type 1 integral. Okay, how do we set this integral up, this double integral? Okay, the y, we're always going to do the y integral inside, okay, for this type 1 case. And we're going to do h2, let's see, we're going to do whatever the upper bound is in our upper limit of integration. We're going to do whatever the lower bound is in our lower bound of integration, okay? And then our function is going to go in here, whatever our function is. All right, so that's our inner integral. And then our outer integral will be the dx, excuse me, the x integral. And what are the bounds here? Are our constants a and b. Okay. Now, there are slight variations of this type 1 integral. Okay, so this would be 1. Okay, so here these constants a and b are kind of clear cut, right? So let's see, going back up to like this case. Okay, we have these two functions giving us our vertical bounds, and then we have these two constants giving us our horizontal bounds. Sometimes those horizontal bounds are a little less clear cut. So maybe, for instance, you're just given this region. You're told, okay, maybe the problem would be phrased like this. Integrate over the region bounded by g1 and 2 and x equals b. Okay. Well, if you look a little bit closer, you see, okay, g1 and g2 cross here and kind of cinch off. So this would give me another horizontal bound, but maybe you have to solve for that that value a. Okay, and then maybe the b is given to you, or maybe we need to solve for both our horizontal bounds. So for these, we need to find our x bounds. We need to find these green dots, the x coordinates of these green dots, these points of intersection. So an example of that would be, let's say we're trying to integrate this function. Okay, so here we're given this general notation. We're told, okay, find the double integral over your region D. And then they tell us the region D is the region bounded by y equals x minus 1, and the parabola y squared equals 2x plus 6. Okay. So it is helpful to be able to draw these regions and kind of get an idea of where you're supposed to be integrating. Okay, so let's see, let's draw our xy plane, and let's draw our domain. Okay, y equals x minus 1. What does that look like? Well, that'd be the horizontal line with y-intercept -1, right? So that's that line. Okay, and then what's y squared equals 2x plus 6? Well, that's a parabola. If we kind of rearrange it, y squared minus 6 over 2 equals x. In other words, x equals y squared over 2 minus 3. Okay, so that's like a parabola that's been shifted back by 3, right? So positive 3, x equals 0. Yeah. Yeah, so that's a parabola that kind of looks like, roughly, it should be something like this. Okay, and let's see. Yeah. So if I plug 0 in for y, my x is -3. Yeah, so yeah. Okay, so the region we're trying to integrate over, okay, what's our one possible enclosed region? It's this part right here, right? Okay. So let's see. I think I might have written this backwards because this is not a function of x, it's a function of y. Yeah, apologies. This is an example from the next section, the type 2 integrals. Okay, so let's put this example aside and we can come back to it in a bit maybe. And let's do an example where we have to find our x bounds. Okay. So how about instead, let's make one up kind of off the spot. Okay, how about let's integrate the function. Let's do something simple. That might not be simple. How about x squared y? Not even more simple. Let's do xy, and let's do on the domain. Okay. How about enclosed by negative x squared plus 4 and y equals x. How about that? Do I like that one? We'll do 0 here. Okay, so let's draw this region. Let's draw this domain. And so we're not really given any information about what our x's should be, right? So to figure that out, maybe we need to draw a picture. Okay, so let's draw our domain. Okay, negative x squared plus 4. If I had y equals negative x squared plus 4, what is that? That's the parabola, the downward facing parabola. Okay, that goes like this. Okay, and then let's see, y greater than or equal to 0 means, well, y is above the x-axis. Okay, so what is our one possible region we could be talking about here? It's this stuff, right? Okay, so this is our region, but the question is, okay, what are our x and y bounds? Or excuse me, our x bounds. What are our a and b? Okay, so I know I'm going to set up my y integral as negative x squared plus 4, and then 0 here. What are my x bounds? Okay, so that's my dy. Okay, so how do I find that? Well, I need to find these intersection points, right? Okay, what am I intersecting? I'm intersecting this curve, negative x squared plus 4, in this line, y equals 0. Okay, so how do I find those points? I set those two curves equal to each other. So I set negative x squared plus 4 equal to the other curve, which is 0. And then I solve for x. So 4 equals x squared. So x equals plus or minus 2. So my bounds of integration should be from negative 2 to 2. Okay. And then the rest is the integrating, right? We would plug our function xy in here and integrate. All right, integrating in terms of y first. So y squared over 2, xy squared over 2, evaluated from negative x squared plus 4 to 0. Okay. We can simplify this if we like. Now integrating in terms of x. Let's see, negative 16 over 8 plus 4 minus negative 16 over 8 plus 4. Looks like it's just 0. Okay. Let's see, does that make sense? Yeah, this is an even function. Yeah, that makes sense. Okay, so this I said was an example from type 2. Let's move on to type 2 now. So we saw that we have these type 1 domains where the upper bound is a function of x and the lower bound is a function of x, and then the right and left bounds are constants. Okay, maybe we need to solve for those constants. Type 2 is kind of the reverse situation. In type 2 regions, our horizontal bounds are going to be functions of y, and then our vertical bounds are going to be constants. Okay. So we have maybe a situation like this. And then again, if we're graphing this as a domain, if we're looking at our domain in the full three-dimensional plane, maybe it looks like this. So as I said, in this case, now the y bounds are going to be constants and the x bounds are going to be written as functions of y. So we're going to have an integral like this, okay, where our functions, we're going to have functions of y. Okay, and now whenever we have functions in our bounds, we need that to be the inner integral, so the inside. Why is that? I'm still trying to, my end result still needs to be just a number, right? I'm trying to integrate over a region. I'm trying to get a definite number out. Okay, so if I had the reverse situation where I had these like functions of x here, and then constants in the inner integral. So let's say I was doing like dx dy. Okay, this would give me a constant, right? This is just a usual definite integral. So this would give me a constant. Okay. All right, and then I'd be integrating a constant in terms of y. So my integral would basically be like cy with these bounds. And then I plug these bounds in and I would end up with a function. In particular, I'd end up with c g1 of x minus g2 of x. Okay, which is still just a function. That's not what I want. Okay, so we see that these functions need, when we have these functions in our bound of integration, they need to be the inner integral. Okay. So again, these type 2 integrals might involve solving for our y bounds, right? So maybe these x bounds are written in terms of functions now, and then these y bounds are constants, but maybe we need to solve for these constants, these green y values. Okay, so an example, x plus 2y, okay, integrated on the domain where y is greater than or equal to 2x squared, less than or equal to 1 plus x squared. And let's see, again, this is I've mixed up my examples here because this will be a type 1. Okay, so let's not look at this one. Now let's go back up to our previous mismatched example. Okay, so let's look at this one. Okay, what do we have? I believe what we should have is this. Yep. Okay, and we could have just as easily written, let's see. And let's just rearrange it a little bit to make it more clear. Okay. So let's use these bounds. So our x values is bounded by these curves. Okay. So this is y squared minus 6 over 2, and this is y plus 1. Okay. So how would I set up this integral? Well, my x bounds I know are given by these functions of y. So let's see. What should be my upper bound of integration? Okay. So my region is still inside this area. I don't want to go any further past than this. I don't want to go beyond this line. Okay. So my x values cannot be, think about your x coordinate. Okay. Your x coordinate cannot be over here, right? So your x coordinate has to be less than this line. Okay. So less than or equal to. So our upper bound for our x coordinate has to be y plus 1. And then on the other hand, our x values can't be over here to the left of this parabola. Okay, so we have to have our x bounds are greater than this. Okay, now that's our inner integral. Now the question is, what's our outer integral? Our bounds for y. Okay, what are these bounds here? They should be constants, but I'm not really given any information about what these constants should be. Okay, I just have to infer their values. Okay, so let's see, y. What's the largest my y value could be? Okay, what's my largest y value in this shaded region? Well, let's see. It would be whatever this value is, right? The y value of this point of intersection. Okay, so that's one of the intersection points of y squared minus 6 over 2 and y plus 1. Okay, and then what's the smallest my y value could be? It'd be whatever this y value is. And again, that's an intersection point of these two curves. Okay, so let's solve for those values. Okay, so I set one equation equal to the other, and then I solve for y. So let's see, y squared over 2. Let's go ahead and break this up. It was y plus 1. Y squared over 2 minus y minus 4 equals 0. Okay, and then it's just quadratic formula, and we can use some of our tricks, like multiplying by everything by 2. Let's see, can we factor this? How about y minus 4 and y plus 2? Does that work? Yeah, that works. So our intersection points are when y equals 4 and y equals negative 2. So those should be my bounds for y. Okay. And then let's see, what am I integrating? I'm integrating the function xy there. Okay, so I've set up my integral, which will probably be the hardest part of these for you guys. And then it's just integrating as normal. Okay, so what am I integrating with respect to first? X. So I get x squared over 2y from y plus 1 to y squared minus 6 over 2. Okay, this could be a little ugly here. Okay. Plugging in my bounds. Let's see. x squared over 2. This x squared over 2, I could have brought out, but we might as well leave it now. X squared over 2 times, oh, I'm sorry. We're integrating with respect to x, right? So yeah, I'm plugging this in for x, my x's. Okay. So let's see, I have y plus 1 squared over 2 times y minus y squared minus 6 over 2 squared over 2 times y. So this looks a little ugly. And then I would integrate that with that in respect to y. Okay. And this is an example in the book. Let's see, let's point out the example. Looks like example 3. And let's see if I've done everything right. I believe so. They brought the 1/2 outside at the start. No big difference there. Yeah, okay, so follow along with it. I'm not going to solve all of example 3 here, but if you would like to see the actual numerical answer for that one, check example 3 in section 15.2. Okay. And that was a bad example. Okay. So once we know how to set up these integrals, maybe we want to know if we can switch the bounds of integration. So in section 15.1, when we had these functions of x and y, remember we talked about Fubini's theorem and how it allowed us to switch the order of integration. So let's say I was integrating with respect to x first, okay, and I had the bounds a to b, okay, and then the y bounds were c to d. I remember we said that we could also just switch the order of integration. So I was integrating with respect to y first. Can we still do that? And that's what we are going to cover next. But excuse me for a moment. So switching the order of integration is still something we want to be able to do even when our bounds are written in terms of functions, but we have to be a bit more careful because we can't just switch them blindly. And that kind of goes back to that example where I showed you, okay, we always want our functions to be our inner integral, right? Okay, because if it's switched, then we're going to end up with a bad result. Okay, so when I have an integral like this, I can't just switch the order like that. I have to do a little bit more critical thinking. Okay, and what's really going to help us is just being able to picture these domains and kind of work with their boundaries a little bit. Okay, so let's say we're given. We could think of this as a type 1 integral. Okay, where our y bounds are written as functions. Okay, so we would have like y equals 1/3 x, and then this we could think of as y equals 0. Okay, we could also think of this as a type 2 integral, right? Where, let's see, if y equals 1/3 x, then x equals 3y, and x equals 3y and x equals 0. Okay, that would be our bounds there. Well, actually, no, not x. X equals 3y and x equals 6. Okay, we could also use these as our bounds, function bounds. Okay, so there's a couple ways to think about this, and being able to switch between the two is going to be helpful. Okay, so let's say we start with we're starting with a type 1 integral. Maybe they give this to us and they tell us to rewrite it as a type 2 integral. Okay. Another scenario is, okay, we figure out what the bounds are for our type 1 integral, but then we try the integral and it's really hard to integrate in terms of y first. So maybe we think to ourselves, hey, maybe this would be easier if I integrate in terms of x first. So we'd like to be able to switch in between. Okay, so that's kind of what I'm saying here. What if it's more convenient to instead integrate in terms of x first? Okay, how can I switch the order of integration here? So what do we want to do? We want to write our y bounds. Right now they're written in terms of functions. We want to write them in terms of constants. And right now the x bounds are in terms of constants. We want to write them in terms of functions. Okay, so let's rewrite the y bounds. Okay, so this is our region, right? Right now we're saying our y is between 1/3 x and 0. That's what these bounds mean, right? Okay, that's fine. But if I was going to write them in terms of constants, how would I do that? What is the largest y value we achieve on this region? Well, it's in this top right corner, right? And what is that y value? Well, if I plug x equals 6 into this equation, I see that my y is going to be equal to 2. Okay, so my y value is less than or equal to 2. And then what's the smallest possible y value I could have here? Well, it's just 0, right? My y doesn't get any lower, doesn't go down here. Okay, so my y is greater than or equal to 0. Okay, so which means I could write my y bounds like this. Okay, so these are going to be my y bounds, and since these are all constants and not functions, I know this is now going to be my outer integral. So I know I'm going to have 0 to 2 dy on the outside. Okay, now I need to figure out what are my bounds on the inside. What are my x bounds? Okay, so that's the next step. Okay, so what functions are what function or functions are the x coordinates bounded by? Okay, so let's look at the left side first. All my points. Think about a random point in here. X, y. Let's call it x naught, y naught. Okay. How does this point? What are my? If this is just like a random point, okay, and think about all the points of that form. So think about x naught, x1, y1, etc. All the x values are greater than or equal to the x values on this line, right? Because all these points in here are to the right of my line. Okay. So our x values, our x coordinates are greater than or equal to the x coordinates on the line. How can I write that inequality? So in some sense, I want to write the x values are going to be greater than or equal to the line, right? Well, let's see. If the line is equal to y equals 1/3 x, okay, let's solve for x there. Okay, so our x would be equal to 3y, right? Just isolating x by itself. Okay, so that line we could rewrite as 3y equals x. And I'm saying all the x coordinates of my points in my shaded region are greater than or equal to that line. So I'm just going to turn this into an inequality. X is greater than or equal to 3y. Okay. So that's going to be my lower bound. My lower bound of integration is 3y. What's my upper bound of integration? Okay, what's the largest, where does my x where do my x points stop? I can't go any further than 6. Okay. So I have this vertical line here. Another way to think about it is this is the vertical line, x equals 6. So my x coordinates are less than, or it's to the left of that line. So I should have x is less than or equal to 6. Okay. So my upper bound of integration should be 6. Okay. All right, and so I put all that together, and that means I can take my original integral, which was this, and if I want to change the order of integration, that's fine, but I need to play with those bounds a little bit and rewrite them as so. Okay. Now my x integral is from 3y to 6, and my y integral is from 0 to 2. And even though these bounds look very different, it's still talking about the exact same region. It's just still two different ways to talk about that same region, that same shaded region. Okay. Some properties of the integrals. Let's talk about some properties of the integrals, and then maybe we can do 1 or 2 problems at the end, example problems. Properties of the integrals, and I put double in parentheses here because all of these properties we've seen before for integrals of single variable functions. There's nothing new here. It's just now we've rewritten it. Instead of writing f of x dx over, whatever, an integral a to b. Instead of writing it like that, we've just written it in this multivariable notation. But these have the exact same properties as our single variable functions. Okay, so first is this kind of additivity. Okay, so if I have two functions, if I'm integrating f plus g on the domain D, that's the same as integrating f on D and then adding the integral of g on D. We also have this idea that we can pull out constants. If I have a constant times my function, I can pull that constant outside. Okay, so you should be pretty familiar with that. And then maybe some more I won't say unfamiliar because they should be pretty familiar, but maybe something you don't, maybe this is more kind of background knowledge, not something you necessarily use very often. But if f of x is always less than or equal to g of x, okay, and let me explain my notation a little bit. I'm writing the vector x instead of fxy. Okay, so this is these things are equal in this case. I'm writing this vector x because this stuff holds in higher dimensions than just 2. Okay, so I don't like writing xy. So I'm just writing the vector x to mean that these properties all hold in Rn, not just R2. Okay. So if f of x is less than or equal to g of x for all x in our domain, then the integral of f is also less than or equal to the integral of g. This number 4 is probably, let's see, numbers 1 and 2 you should be pretty familiar with, maybe already kind of know intuitively. Number 3 you may or may not use very often. It's good to know. Number 4 might come in very handy. So what if we were given, well, let's first talk about number 4 is, let's say D1 and D2 are two regions that only intercept, maybe they never intercept, or maybe they intercept just on the boundary. Okay. Then what does this symbol here mean? Okay. On the left side. Okay. So the integral, this is the integral of f on the union of D1 and D2, which is just a fancy way of saying both D1 and D2. Okay. Excuse me. So let's say this is D1, this is D1, and then this here is D2. Okay, D1, D2 is just the whole thing. Okay. So if I wanted to integrate, let's say I was given this domain. Let's say I was given this domain in the XY plane. And I was told to integrate on this domain. Well, maybe integrating on this entire thing all at once is difficult, but this property says, well, you can just split it up into the two separate integrals. So you can integrate here on D1 first, okay, and get a number. Then you can integrate separately on D2 and get a number. And then you add them together and you get the entire integral. Okay, so fairly straightforward. But why would you possibly do that? Well, maybe, as I said, maybe integrating on the whole region all at once is difficult. You know, what if I was trying to, what if part of the problem was coming up with the bounds of integration? Okay, that'd be kind of difficult for this case. Let's draw it a bit more clearly. Okay, so let's say it was something like this. And I was told to find the bounds of integration for that. Well, it's kind of weird because, okay, you could probably do it straight away, but let's say you wanted to do it in kind of this form. Okay, let's say for some reason you wanted to integrate with respect to y first. Okay, what is your upper bound for y? Well, in this region, it's just this constant here, whatever this constant is, right? D, upper bound D, lower bound C, and on this piece. But then in this piece over here, well, the upper bound is this line, and the lower bound is this piece. So maybe the way you would do this is you would kind of split this integral up into two. Okay, you would do the integral for this piece. Okay, and let's say this is the line y equals 2x plus 4, and this is 1. Okay, so maybe your upper bound here would be 2x plus 4, 1, and then this is, let's say, 1 to 2. Okay, 1 to 2. Okay, so this integral would give you this first region. Okay, and then let's see. One to two, let's see. Yeah. What is the integral on this region? Well, let's see. Now, once I'm on this region, this is just a rectangular region, right? So it should be all constants. Let's see. So my y bounds would be what? 1 to 8, because this upper line is 8. And then my x bounds would be from 2 to whatever this line is. Let's call it 6. Okay. And then I just integrate whatever my function is on these two separate integrals and add them together, and I get my final answer. Property 5 is just sort of a, you would call it a monotonicity property. Okay, if f of x is always greater than or equal to little m, and it's always less than or equal to big M, then the integral of f, we could do this step by step. The integral of f should be greater than or equal to the integral of little m, and it should be less than or equal to the integral of big M. Okay. Well, this is just a constant, right? We're integrating a constant, so we get m integral of dA. Okay. Now, what is the integral of just, I could think of dA as 1 times dA. Okay. What is the integral of 1 on a region D? Okay, just the number 1. We could think of it as the constant function 1. This integral is going to give me the area of D. And that kind of makes sense, right? Because I'm thinking about, my region, it has some surface area, and then I'm basically multiplying by f, which is the height of my rectangles to get like a volume. Okay, so if the height is 1, if the height is always 1, what's the volume of the box? The volume of the box is just the area of the base, right? But cubed instead of squared. So we have this integral of the constant will be little m times the area of our domain. Okay. And on the other hand, the upper integral, this upper bound, will be large M times the area of the domain. Okay. And then in the middle, we have our integral of f. Okay. So that's really all the material for this section. I would like to now take the opportunity to just, let's do one more example. Let's do number 18. All right, let's see. What problem should we do? Why don't we do number 18 from the book? And this will also kind of bring up a point that might have gotten lost in translation. So we're told to integrate this where D is, and they phrase it like this: D is the region bounded by y equals x, y equals x squared, and x greater than or equal to 0. Okay, so we've talked about type 1 and type 2 integrals, or type 1 and type 2 domains for these double integrals, these iterated integrals. And we've talked about switching back and forth, but maybe kind of fundamental to all that is just being able to look at a region and set up an integral for it. Okay, and that's really what all of this stuff boils down to. So let's try and draw this region and then come up with some bounds. Okay, so I'm going to draw my xy plane. And then I'm going to consider my bounds that I'm given. Let's see, y equals x. That's this. Y equals x squared. What is that? Well, that's the parabola. That goes here. Goes like that. And then let's see, the line keeps going like that. And then we're told, well, x is greater than or equal to 0. Okay, so that means we can't have anything over here, right? So what's our one possible region? Well, the one possible region we have is this thing. Okay. All right, and there. Now, what bounds could I write for this region? Maybe I want to do an integral like this, where, okay, I'm integrating the bounds for y are functions. And then these are constants. Or maybe I want to do it the other way. Okay. Well, looking at this is one way better than another. It looks like we could probably do this one either way. It's really about what kind of pops out to you, and maybe just getting a little bit of a feel for it. So my tendency is to do this type of setup, type 1 integral. It's just naturally easier for me, just because, like all of you, I have so much more experience working with functions like this, g of x and h of x and f of x, things like that. So that's kind of my natural tendency. Okay, so if I wanted to do this type of setup, okay, let's my first step would be to find my my functions. I'm looking at my bounds for y, and I want to write those as functions. Okay, so what let's see, this is y equals x, and this is y equals x squared. So what function is the bound for my y values in this region? Well, let's see, all of these points, the y values are less than this line, right? So what is the line? It's the line y equals x. So the function I should put in for my upper bound is x. What about my lower bound? Well, let's see, it's everything's greater than x squared, so I should do x squared. Now the question is, what are my a and b of my region? Okay, well, those are going to be the constants, the kind of the furthest points of my x values. Okay, so what's the furthest left to the furthest to the left that my x values go? Well, I stop here, and what is this? This is x equals 0, right? And then what's the furthest to the right I go? Okay, and how did it, by the way, how did I know this is x equals 0 besides just looking at it? And how can I find this point here? How do we find those 2 points? What I do is I take x squared. It's where these curves cross, right? It's where x squared crosses x both times, right? So I set x squared equal to x. And you got to be careful here. If you just divide, right? If you just divided an x from both sides, what you end up with is x equals 1. And that's part of the answer, right? These curves intersect when x equals 1, but they also intersect over here at x equals 0. So the safer way to do this, when you have like terms on both sides of the equal sign, move everything to one side of the equal sign. And then factor or use quadratic formula, however you prefer, and you get 2 solutions, x equals 0 and x equals 1. So our bounds should be 0 and 1 for x. And then let's see, what's the function I'm integrating? X squared plus 2y. Okay, so first I integrate in terms of y. And what do I get? Okay, now I evaluate my integral at my bounds. Let's see, so I'm plugging x in for y. Let's see. Okay, I get this. Let's simplify. So I should end up with this. And then integrating that, let's see, I would get, in terms of x now, what would I get? I get negative 2/5 x to the 5th plus x to the 4th over 4 plus x cubed over 3, evaluated from 1 to 0. What would that be? Let's see, negative 2/5 plus 1/4 plus 1/3. So whatever that is, finding the common denominator, etc., simplifying. Hopefully that's right. It's one of the even numbers, so I guess we'll just have to trust me, huh? If you guys come up with something else, let me know. That's all the material for this section. I imagine it's going to be something that's a little hard to get used to. It's a matter of practice. All right, good luck.